Good afternoon, everybody. This session is advanced topics in ParaView. My name is Dan Litsa. I'm a R&D engineer with Kitware, and I'm gonna teach this class. So these are not necessarily advanced, but maybe less often taught topics in ParaView. So we're gonna teach two distinct topics. One is gonna be user-defined filters, and as a prerequisite for that, I'm gonna cover VTK data model and Numpy integration. So all that stuff is used when writing your own programmable filter or Python calculator. And the second topic, distinct, is going to be physically based rendering and ray tracing. So this is like more advanced rendering that is available in ParaView that will allow you to create more visually appealing visualizations in ParaView. So I'm going to be using ParaView 5.9.1. This is required for the second part, for the advanced rendering part. The first part, probably you could use any recent ParaView, but it's easy enough to just download the ParaView, the latest version, and use that one for this presentation. So let's start with VTK data model and Numpy integration. We have available documentation for learning more, for getting into details about these topics. So the first link I have here is the C++ documentation. This is VTK documentation. So even if this is a ParaView tutorial and you do program inside ParaView, this is VTK programming. So this is distinct than the ParaView scripting that is also available. We touched a little bit on that in our first class 2 days ago on Tuesday. So this is VTK programming. That's what you need to create your own filters. So this C++ documentation points to the VTK documentation. This is where you find out details about filters and their API. Then I point you to a README file that is the Python wrapping README file. This shows you how you translate the C++ API into Python API. So you have some simple rules. It's very close for people that already know or check out the C++ documentation. It's an easy translation to Python. This document gives you more details about that. Then we have two textbooks. The visualization toolkit. This is a visualization textbook. So it goes into details and when discussing various visualization algorithms, and it uses VTK. So it's a very good resource for learning more about how things are done in VTK. The VTK user's guide, it's a user guide. It's so visualization textbook, visualization VTK textbook. This is placed on the web. The original author put a lot of work and translated all the examples into the modern VTK. So all this is available on the web. So it's a very nice resource. The VTK user's guide, that's a user guide for the API. It's still a very useful resource, even if it's an older resource, but for an overview, it's a great resource to learn about VTK. Even if it talks about an older version of VTK, it's still good as an overview. And then we have probably thousands of examples. I haven't updated this link. It points to the old site, but just search for it we moved it into Kitware website. Initially was in the Bill Lawrenson's personal GitHub. So we moved that into Kitware website. So just search for VTK examples. We have like thousands of examples, and they are very nicely organized on categories. Bill did a lot of the work for that resource as well, and you know, a lot of other community members as well.
Apologies, Dan. Apologies.
Yep.
Sorry, yeah, sorry to interrupt. Are you sharing something at the moment or not? Because there's nothing appearing on the screen.
Yes. Oh, maybe it's.
Yeah. Can you please try again?
Yeah. Let's see. So I do have a share screen. It is. Or let's see. Let's try now again. Thank you for letting me know.
Oh, okay. It's coming now. All good.
Okay. Yeah, I don't know what happened. Maybe the sharing was stopped. So yes. So I guess I didn't cover too much. I have a number of links here that I talked about. These are links to the C++ documentation, the Python wrappers, and the 2 textbooks, VTK textbook and the user's guide, and then a link to the VTK examples. Okay, so sorry about this issue. So let's go over the VTK visualization objects. So there are 2 kinds of objects that are used in ParaView. VTK has a few more types of objects. So in ParaView, when you write your own filters or your own user-defined filters, you're going to use data objects that store data, provide access to data, and compute information, particularly to the data. And you're going to use algorithms or filters in ParaView terminology that ingest, transform, and output data objects. There are 2 more types of objects in VTK we won't deal with: rendering objects and widgets, interaction objects. So you don't use these in ParaView, so you don't need to know about them when you write your own filters. So let's look at these 2 kinds of objects, the VTK data objects. So the most basic data object that is used are VTK data arrays. So these are just arrays of ints, floats of various types. And also they have accessor methods. So let's see. And then a data object is an object that has a number of these data arrays. Yeah, and the data set is a data object, so it's a object that has a number of arrays, but also it has geometric and topological structure, so that is, it stores in a certain way the points or the nodes of the data set, and also it stores cells for the data set that is interpolation information for the data set. So that is connection between points. And all this information is stored using data arrays. Yep, so in this picture here on the right, I show 4 points, and the cell is the connection between points. This is used to find values for positions in between the points. Yep, it's often the case that when you do a visualization, you will need to find out the value in between the points, and you do that by interpolating using the cell and find out the value from in between the points. This is a hierarchy that shows you the VTK data objects. So everything in VTK is derived from an object. This provides reference counting. So we provide reference counting so that we help with memory management. If you have pointers from various places, we count those pointers and ensure that once an object is not referenced, it is deleted. The data object, as I said, it just stores a number of arrays, and then the data set stores this additional information, geometric and topological information. And then we have different types of data sets that provide optimizations for specific organizations of points and cells. So the most optimized and often the fastest data set to process is what we call VTK image data or rectilinear regular grid. And then rectilinear irregular grid, we call this VTK rectilinear grid. Structure grid, this is also called the curvilinear grid. Polydata and unstructured grid. So we're going to cover this in more detail in the next slide. So the image data, it's a uniform rectilinear grid. The topology and the geometry is implicit. So what this means is that we don't need to store point positions and we don't need to store cells. All that stuff can be computed. The only things we need to store is the origin of the data set, the dimensions, that is the number of indices along each axis, and the spacing between the points. And then you can compute the position of every point, and also by using neighboring information, you can you know the neighbors and you have the cells this way as well. The rectilinear grid, you have to store a little bit more information. So you store the origin, the dimensions, that is the number of indices along each axis, and the spacing along each axis. The curvilinear grid, you have to explicitly save points. The topology, so you still store the data set in a 3D array, but the point positions can be anything. So think about this data set as the previous one, as the rectilinear grid, where you deform the grid. So you just move the points anywhere. Yep, so this is, you store a little bit more information here. The most general data sets are the polydata and the unstructured grid. Here, both the point position and the cell structure are implicit, so they are explicit, so they're explicitly stored. So this consumes a lot more memory, and often it's slower to process. The difference between polydata and unstructured grid is the unstructured grid can store 3D cells. The polydata does not store 3D cells. The polydata is designed so that you can send it as fast as possible to the graphics card. This is what we use to send to render data. So once you have the data set, that is the point positions and the cells, you often store attributes with the data together with the data set, such as pressure at each point, temperature at each point, and so on. So you have different types of attributes. You can have scalar attributes. This is just one scalar value. You can have vectors. You can have tensors, normals, texture coordinates. So all these are types of attributes that you can store in a data set, and you can store it for each point, or you can store it for each cell. So we have two types of attributes in a VTK data set. So again, in VTK terminology, points are the same as nodes in other domains, and cells are the same as elements in other domains. This is another diagram that shows you the object modeling for the attributes. So you start here. This is a data set that can have field data. So the field data are arrays that are not associated with either points or cells. So they can have any number of elements. And then this is the object hierarchy. So a field data has any number of arrays, and then from that we derive the data set attributes. These are more constrained. They have a set number of values. And from this, we derive cell data and point data. So the cell data has as many values as you have cells, and point data has as many values as cells. So these data set can have has one cell data, one field data, and one point data. Yep, and each of these can have any number of arrays, so any number of attributes. We have here a table as well that can have rows and columns. So the VTK data array, the most basic storage object in VTK, is just an array of tuples. So you have n tuples or any number of tuples. Each tuple has a number of components. So scalar arrays have one component with n tuples. Vector arrays have n tuples. Each tuple has 3 components. Tensors, each tuple has 9 components. Yeah. So let's look at how you convert. So VTK has a mechanism or API to allow you to easily switch between Numpy and the VTK objects. This is useful by itself. Often people do computation in Numpy, and then they would want to maybe show or do additional computation, additional processing in VTK. We make it easy to convert between Numpy and VTK, and that conversion is done using 0 copy, so no actual data is copied, only pointers are transferred. The only issue, the only thing you have to be aware of is that VTK, so for one, the array doesn't matter. We're going to mention this later on. For multi-dimensional arrays, it does matter. So the issue is VTK stores data or multi-dimensional arrays in Fortran order. Python and C++, they store them in C order. So C order, that's along rows. Fortran order is along columns. So you have to be aware of that if you convert multi-dimensional arrays between Numpy and VTK. In this first example, I don't think this matters. So let's look at this first example. So we create a Numpy array. Yeah. And then we use this Numpy support.numpy to VTK to convert into a VTK array. And then we use VTK API. So X is a VTK array. All VTK arrays have names, so we can set a name for that. And then we use VTK API to introspect that array. So we get the data type, and we print all that. So the data type, the number of tuples, and the number of components for each tuple. Yep, and we print the actual values as well. Yeah, so we get the fact that we have the type is 11. You can see the correspondence between the numbers and the names in this header file, and probably that's float. We have 2 tuples, each tuple, so we have 2 rows, each tuple has 3 components. Yeah. And I have a few more notes here. the shape N with nothing here corresponds to n tuples and one component, and C corresponds to n tuples and C components. Yeah, you can execute this kind of VTK scripts even using ParaView using PVPython. Yep, so you can execute small VTK scripts this way. So you can try all these examples in here. I'm going to add a note in the Q&A and point you to where I will store the slides if you would like to look at this later on. So as I mentioned, you have to be careful when converting multidimensional arrays between VTK and NumPy or even VTK and C++. VTK uses Fortran order. So the X dimension increases the fastest, following by Y and followed by Z. So you know, this is kind of tricky to figure out. You can look at it and understand this better on your own, but keep this in mind. So we looked at conversion between arrays and NumPy. VTK dataset, so this is the access to any of the datasets that I mentioned, has also a nice interface that can be accessed in using sort of more Pythonic way. It's integrated with NumPy as well. So let's look at some small examples where we create some VTK datasets and then we access them using this interface. Yeah. So we're going to create a sphere using the VTK Sphere source. That's how you access the sphere source. So VTK Sphere source. This creates a polygonal data. Yeah. And then we are going to apply the elevation filter. The only thing this filter does, it creates another scalar that contains the elevation. And that elevation is computed using a default direction, default vector. Yeah, so the lowest along the vector has small values, and then toward the tip of the vector has high values. So we make the connection between these filters. So that means the elevation filter is going to be applied to the sphere, to the polygonal data created by the sphere, and then update does the processing. You can recognize this in ParaView as well. You always have to press update. So this executes the pipeline. Yeah. So this created another data set that has this elevation scalar. We're going to use this wrap data object to create a nicer interface, a NumPy interface or a more Pythonic interface to the VTK dataset. So sphere is the wrapped object. And notice right now we can access the arrays, the point arrays, using a map interface. So you can say sphere.pointData.keys. So these are all the arrays that are all the names of the arrays. Yep, and then you can access the actual data array using this map interface. Yep. So you get that the data set will have two scalars. And then when we print the elevation scalar, you get a number of values here. Yeah. So you have a nice, more Pythonic interface to the dataset array. And this interface is used in the Python calculator and also in the programmable filter. So a few more examples here. If you get the elevation, so that's the array created by the elevation filter, you will notice that the type of this array, so you'll notice that this array is a NumPy array. So that's a type of the array. It's a dataset adapter VTK array, but that is derived from the NumPy arrays. So it behaves like NumPy arrays. You can use it anywhere you could use a NumPy array. So this gives you like a nice, powerful functionality to use the VTK arrays as NumPy and use them in NumPy algorithms to get like a quick computation for your data. Few more examples that show you exactly that. You can what we do here is we create a new array by using this NumPy syntax, elevation +1. This is NumPy syntax that creates a new NumPy array, and we append this to the Sphere dataset. So we use the NumPy interface and this simplified interface to create another VTK array. Yeah. And then you can find out the maximum value from this array. You can find out the maximum value from the newly created array. And then what we show in this third print statement, we show that the sphere, which is the wrapped object, has also a pointer to the actual VTK object. Yeah, so you can use that, and we will see you will need to use that when you create a pipeline. Yeah, so we will see an example of that. So this prints the maximum for elevation is 0.5. The maximum for the newly created array is, as expected, 1.5. Yep, and we print the polydata, which shows that we have exactly the arrays we expected. So E+1 is the newly created array. Yeah. So let's see. We have another example here. This shows you that we have a number of algorithms in VTK that some of the algorithms match the names of algorithms in NumPy, but they are more powerful. So let's look over this example. So here we create a VTK RT analytical source. This is the wavelet. If you watch or if you looked around in ParaView, we have a filter core wavelet. It creates like a wavelet image data, wavy image data. This is that wavelet filter. That's how it's called in VTK. And then we transform that image data into an unstructured grid. So this is what the triangle dataset triangle filter does. We do the connection, so we create a pipeline. So here we just create the objects, we connect the pipeline. The actual processing happens when we call update. Yeah, and then we create this wrapped object for the unstructured grid. This is the data. So this is an unstructured grid. Remember, we converted that to an unstructured grid, and you can call gradient. This function uses the grid, the unstructured grid, to compute the gradient. So it uses the connections between points to compute the gradient. Yep. So here we print the values, and also we print the fact that the RT data. Let's see. So RT data.dataset. So this here we show that the array on which we apply the gradient processing has a pointer to the actual data set, because it needs the data set to know the connections between points. Yeah. So that's what we show here. And we restate this. The array has the data set field. It needs that to compute the gradient. So some of the algorithms, in this case gradient, use the mesh. A few more examples. So here we have the sphere and then the elevation filter. We create the pipeline, make the connection, and then call update, and then create the wrapped object. When we print the sphere, that's a dataset adapter.polydata. The type of the object is VTK object wrapper. So that's true. And the sphere has a pointer to VTK object. We mentioned this before. So wrapped object has a pointer to the actual VTK object as well. So you can call VTK API functions, methods through the wrapped object, but when you pass it to a pipeline, you have to pass the actual VTK object, not the wrapped object. So that's what we show in this additional example. So here we shrink the sphere, the triangles in the sphere. We want to do that, so we create the shrink filter, and then if we try to pass as the input connection of the shrink filter the wrapped object, we're going to get an error. So what you have to do is you have to pass the actual VTK object, not the wrapped object. Okay. So we covered this before. This wrapping allows you to nicely access the attributes of the data set. So you can use .point data, that's a map between the names of the arrays and the actual arrays. Yeah, so you can see all the names using the keys method. And what we see here is that the we have 2 point arrays and we have no cell arrays. And then here we can print the point data array. Remember, this is also a Numpy array. Yep, so that means you can do Numpy tricks, such as just print the first 5 elements of the array. Yep, so you can do any Numpy tricks on these VTK arrays. So that's pretty cool. Okay, so this was kind of the introductory part for these user-defined filters. So this is the way you access VTK objects and VTK arrays in the programmable filters and also in the Python calculator. Yep. So the ParaView user-defined filters also includes the calculator, which is a simpler interface, but so the calculator and the Python calculator, these first 2 filters allow you to compute derived attributes out of existing attributes. So calculator provides you like a calculator interface that allows you to use a formula and compute a derived attribute. So you can access existing attributes using these controls, scalars or vectors. And then you can put a formula in here and then specify what's the array name result and compute the value. So in this example, we also checked the fact that these are coordinate results. So calculator can produce coordinate results, that is the points of the data set. So this is a way you can change how your data set looks like. In this example, we created a number of random points, like a point cloud along a sphere, and then we flatten the points. So we use the x and the y coordinates, but we threw away z. So z is going to be 0. So this will flatten the data set. We can try this out. Yep, so we're gonna, if you have ParaView started, or you can start ParaView, and I'm gonna use control space to create a point source, to look up the point source, enter, yep, and then we have the center here. You specify the number of points, you can say, I don't know, 100, yep. See. Radius, we have to specify radius. Let's put that 1, let's say. Surface, let's see, points, maybe point Gaussian. Okay, so you start to see here things. Okay, so what I did is I use the point Gaussian representation to show the points. He thinks it's a 2D data set, so let's click on the 2D so that it's a 3D data set, so I can rotate it. Yeah. Okay, so I changed the number of points and I changed the radius, and also I specify this is a 3D data set. Yeah, and then we can do the calculator and enter the formula we have in the slides. So I'm going to use x times I hat plus coordinate y. You can type that times j hat. Yeah, and that's going to be coordinate results. So press apply. So notice now we got rid of the z coordinate. Yeah, so this is flattened along the z axis. I don't know if you can see me interacting with the data set. I think there's slight delay, but yeah, that's how you flatten the data set. So that's this calculator example. Okay, Python calculator does the same thing, but it allows you to use Numpy when you compute your formulas. It cannot do coordinate points, so that's why we kept the calculator around as well. And also cannot compute normals or texture coordinates. So what you do here is you type your expression, and the Python expression, the way you access the arrays, it's exactly what we've seen previously. So you can type, for instance, your expression is 5, and if you say that's a point array, you'll get an array that every value is going to be 5. Yeah, you can access arrays sort of in a even more streamlined way by just using the name of the array. So normals, you can do that. This is the interface we've seen earlier. So inputs of 0, that's the input to your filter. It's 0 because a filter can have several inputs. Dot point data, and this is accessed as a map value. So this is the interface we've seen earlier. So we can try this. Let's try this for, let's reset, yeah. And let's try this for the sphere. So we create a sphere. Yeah, and then we use the Python calculator. So we have the expression that we have to enter here. So let's use this one, a sine of normals plus 5. So this creates a new array called result. Okay, let's color for on this array. So it doesn't vary that much. So let's see. Let's try this one, area of inputs of 0. So this is the area for each. Let's try this one. Yeah, no, that's, I was wondering why. I think this is a mistake here. Oh, that's a step. Okay, let's see. And then, okay. So this computes the area of each cell in the data set. So what I've done is I created like a cell data, cell array, and then I also rescaled so that it's you can see the colors. So I rescaled to the actual range of scalars. Yeah, so these triangles are bigger than triangles at the top. Okay. The last example here, it accesses the point array, so all the points, but only the first components, only the X components. So this creates an array where the values of the array are the X components for your points. Yeah. So, okay. So this area is a little trickier because you don't really see what the actual input for the algorithm is. Okay, so another example, you can compare different data sets. So in this expression using the Python calculator, so in this expression, we look at the first input and you subtract from the first, from input 1, input 0. Yep, and so this is like a syntax that specifies that you use the iteration array, the iteration point array from input 1, subtract from that iterations array from input 0. Yeah, so you subtract these two arrays and you get another value. So this is the way to compare the two data sets. Okay. So the mesh from the first input, it's always copied to the output. So what you do here is you only compute new arrays. The mesh is going to be from the first input. Okay, so let's look at the programmable filter. So I think, let's see. So this allows you to write any VTK filter inside ParaView. So let's start with the simple one. We look at the input, we store that in a variable, and then we compute a new array by using the interface we've just seen. So we read the array called v, the point array called v, and divide that by 2. So this is similar with the calculator, but we do it as a programmable filter, as the first example. And then we add this new array to the point data for the output, and we add that to the output. Yeah. So this is the request data or the computation path in the VTK pipeline. It turns out that the VTK pipeline has additional passes. A filter is called at additional times besides only to do the computation. So there are two more important pipeline passes when the programmable filter or any VTK filter is called. One is request information. So this allows the filter to provide information about the data that will be produced. This information can be the number of time steps and the time values for each time step for temporal data sets, or the extents for image data. So think about this like a reader that maybe reads just metadata from the data set and provides this information ahead of time, ahead of computing, reading the whole data. So this allows VTK to do things like streaming. So, and also to provide information ahead of time. A request update extent, that is a pipeline path that propagates subset information upstream. So basically think about the streaming where you want to read only a piece of the data. So the way this works is each filter receives from the output what's the data required, and based on that is going to pass that to upstream to its input filter, what kind of data, what kind of subset it needs. Yep. So it receives what is required from downstream, and it passes upstream what it needs. So that's the request update. And request data is the actual processing. So for a reader, that would be reading the actual data. So we have a couple of examples here. So let's see. So this is reading a CSV file into a table. So this is the script path or the request data path. Yeah. So in this case, we just read the file, We do that by using this Numpy function, get from text, that reads the whole file into a series of arrays. And then we go over the columns, the names of the arrays. We read each array, and then we add that array to the output. Yep, and we use the syntax we've seen. In this case, there is no point data or cell data, there is a row data. Yep. And we append the array with the name given. Okay. So it's a lot going on here. Arrays are Numpy arrays, but you can send the Numpy arrays, you can set Numpy arrays directly to these wrapped objects. So it makes it fairly short, fairly easy to mix Numpy and VTK processing. And you can use that in these programmable filters. So let's look at another example. This is an example that reads CSV file series. So the trick here would be to provide the information about how many time steps you are reading. Yep, so we have to write two time steps, two pipeline passes in this case. This is the request information. So let's see what we do here. We define a function and then we call this function. So basically what we need to do is specify to the pipeline that we have 4 time steps with time values 0, 10, 20, and 30. And so that's what we do. And in here are the gory details on how we do that. Filters, VTK filters, communicate with the pipeline using these information objects. So we're gonna get the output information from the executive. So the pipeline executive is the object that executes the pipeline and manages the communication between filters. Yep. So we get the executive and we get the information. We remove this information about time steps, and then we add the new information. So we add this information to the output information. So we append this special information called time steps, and then we add these time steps that we receive as a parameter. So that's an array with 4 values. So we're going to add each time step. And then we add also the range, that is the first time step and the last time step. Okay. So in here we just specify how many. We don't show how do we get this information, but if you if you write a reader, probably you will look at the files and maybe you look at the sort of parse the file names and figure out that you have 0, 10, 20, and 30. These are the time values. Yeah. And then the script pass or the request data pass actually reads the data. So let's see what we do. So this pipeline execution function or the request data function, it does 2 things. It receives from the executive or from the user, it receives information about what time step is needed, what's time step required from the pipeline, and then it reads that data, it reads that time step, and then specifies what was the time step that was read. So in ParaView, you sometimes see this where maybe you have several data sets and you don't get the time step, when you read the time step, you don't get exactly what you requested. You get something that's close by. When for instance, you have two data sets that have slightly different time steps or time values. So let's look at this. So this function talks to the pipeline, talks to the executive, and figures out what is the requested time step. Yep. So we get the information object, and then this update time step tells us what is the time step that it's requested. Yeah. So that's a requested time step. And after that, we read the actual data. We set that data to the output, and then say that, well, if we didn't read that time step, but we read some, or that time value, we read something close by, we have to say what we read. So we set the data time step to the value that we actually read. Yeah. Okay, so let's look at another example. So this is the reading binary 3D image. In here, you have to specify in the request information, you have to specify the extent of your data and the spacing, and also the origin. If it's, I think in here, we just, it's 0, so we don't specify that. But in general case, you have to specify that as well. So you do that by using these information objects. So you set the whole extent to be this one, and you have set the spacing to be this one. Yeah. And then you read the actual data. So we read the raw data. We know the data type of the data. We use Numpy to read that data. You have the dimensions are also read from the file or known. And you have to set the extent of the data, and then append the data to the output and set the active scalars to be the array that you just created. Yeah. So these are the programmable filter. Some examples of the programmable filter. There is another way to create these, to create your own filters. These are the Python algorithm. So instead of embedding these filters into your ParaView processing pipeline and then saving that, the only way to save those programmable filters are to save them in a state file. So that's not ideal. The editor is not that nice. So an alternative way is to use these Python algorithms. So these are entire Python files. They look a lot more like the VTK filters. They are entirely written in Python. You're gonna write the same processing steps as what you've seen. So you'll have request data, request information, request update extent, but they are all added. They are all in the same class. You can also create UI for your filters, either by using XML or using like a Python annotation. So check this out. We have a couple of examples at this link. Okay, so let's see if there are any questions. I'm gonna switch to, okay. So there's a number of questions. I'm gonna try quickly to look at these questions. I think we are running late, but Yes, I'm going to add the PowerPoints as a link to this discussion. So after this finishes, I'm going to add the PowerPoints there. Oh, ParaView 5.4. I don't know. So yeah, I recommend use a more recent version of ParaView. So the Pythonic interface works for any OpenFOAM. It works for the meshes, like either unstructured grid or so it works for any meshes. I guess the advantage of using this Pythonic interface is that you can use Numpy to do quick computations, to compute derived attributes. Yes, so I'll point. I apologize. I'll post the presentation to a common somewhere on the internet and post a link. Okay, so okay, let's go on to the next part. This is completely distinct from the first part, but it's also something that we don't teach that often. So this deals with advanced rendering in ParaView. There are two ways to get more advanced rendering: physically based rendering and ray tracing. So why would you want to use those? Well, so visualization has two goals. One is to understand better your data, gain insights into the phenomenon studied, but also to present your results. And when you apply for grants, it's often useful to have engaging visualizations. So that's what we're going to look at: how you're going to build a more engaging visualization using ParaView. And we're going to look over simple examples that just show you how to get started there. So physically based rendering, this is a way to compute lighting in ParaView and other applications. It creates a more realistic rendering, and also it has more intuitive way to specify rendering parameters. So instead of specifying specular, ambient, and diffuse parameters, the diffuse color stays, so that's the color of your object, but we use roughness, how rough is the surface of the material is, and metallic. I guess metallic 0, that's more like plastic. Metallic 1 is more metallic, you have more reflections there. So different parameters and also different lighting equations. There is not much difference in rendering speed. So the rendering speed is the same. That's because of everything is done in shaders. So there is not much difference in rendering speed if you use the classical raw shading or physically based rendering. So in this presentation, we're going to cover as much as we can. We have small examples. I'm going to start with first the picture that we're going to get, and then I have in the slides kind of the operations you have to do to get that picture. So to get this torus with colored with physically based rendering, basically the main part is you have to set the display parameter to be physically based rendering, or PBR. So remember, display parameters refer to, well, they apply to selected data and selected view. So that means you can mix and match objects rendered regularly or with Guro and objects rendered with PBR. Yep, so let's try to do that. So I'm going to start with the torus, or this is super quadric, yeah. I'm going to make it more rounded, so I'm going to change the theta resolution and phi resolution. Apply, yeah. And then change the display property, interpolation. So you can do that by searching. So lighting interpolation, that's a display property, which is that PBR. Notice the way it looks completely changed. And then metallic and change the color. Yeah, so it's kind of hard to find these properties. So make it metallic and change its color to, so edit color map, change its color to this orange. Yeah. Okay. So I think some of these properties are advanced, so if you cannot find them, make sure you toggle the advanced properties. Yeah. So you can play with the parameters here. You know, if you play with the metallic parameter, well, here I think I switched between Guro, flat interpolation, Guro interpolation with specular 5, and then PBR. Yeah. And also you can, this works if you do color mapping as well. Yeah, so we can play here with this stuff. Flat, you can see the actual the actual triangles. Guro can set the specular a little bit so that it has some highlights, and then PBR looks completely different and arguably more engaging. Yep, you can change the coloring, normals, let's say X. Yeah. Okay. So you can use textures to set various parameters for physically based rendering. That happens for Guro as well. So you can set color. You can also set roughness and metallic. You can set normals as well, or normal mapping that allows you to perturb the surface, the rendering of the surface, so that you simulate small textures in the model. So this is this example here is done by using a texture and applying that to normal mapping. So you don't need to use like triangles to model this roughness. Yep, or the pattern, the VTK pattern. You can do that with the texture. Occlusion mapping, so that's another texture that you can use, allows you to specify what areas receive less light, and you can use that to accentuate perception of cracks or faults in your model. So I think left uses occlusion mapping, right doesn't. Yeah. So we're going to look at a small example. Here, I will add all the materials for the presentation to that common location after the presentation. I have a link here to a number of examples. So this is one of the examples here, this bottle. This is how the example will look after we are done with it. So let's reset. And then we're going to load the models here. Let's see. I think this is where it is, water bottle. It's a GLTF file. So in the latest ParaView, GLTFs work directly. I think in previous versions, you have to use like a plugin. Yeah, but the latest ParaView, it works directly. You don't need a plugin anymore. So apply. That's the bottle. You can apply the normals. So right now we use the regular rendering. Yeah. So the guru. Let's see. Okay, normal texture. The water bottle. Normal. Yeah. So you see something change here. I don't know if you have the enough resolution, but it doesn't look right. Normals can be flipped in different models. So we have a checkbox here to flip the texture if it doesn't look right. And now it looks right. You have some triangle here, some mountains here on the bottle. And then let's see why. You have some writing here. Yeah. So if you keep Y pressed and move the mouse up and down, you can rotate around the Y axis. Okay. You can use the normal scale to accentuate the changes. Yeah. So you can load the color. So let's see. This is the regular texture base color. Yep. So this is the regular rendering. If you change this to PBR, interpolation, it looks shinier, but you lost the color. The reason is that the color is called differently in PBR than it is in the Gouraud shading. So the Gouraud shading is called texture. Here it's called base color texture. So you have to set that again. Okay. And then you can set occlusion, roughness, and metallic. So you set additional parameters using the texture for the materials. Yeah. So now it's you set the metallic parts, the roughness as well. And then the last texture you can set is the emissive texture. And this allows you to see this emissive property on the bottom. Yeah. So if you look at these textures, you'll see basically the color that's applied to the bottle, the normal, these are the patterns that you see on the bottle, emissive texture, and also occlusion, roughness, and metallic are sort of packed into the same texture. Yeah. So in the RGB component. So the occlusion is in the R component, roughness in the G, and metallic in the B for the RGB components of this texture. Yeah. So this is PBR. PBR allows you to also use images to light your models. So if you wanna, you have like a visualization and you wanna present that into a certain environment, instead of modeling that environment, you can use this skybox. So just find the skybox that you like, or you can take pictures. There are apps that allow you to create your own skybox. So you're going to use this environment to show your visualization or your model. So it's a lot easier to do that instead of modeling an environment. So this is how these images look like if you load them into an image editor. They don't look like these 6 squares because they are packed using this equi-rectangular projection. So this is done to save space. Yep, so the latest version of ParaView supports HDR format as well. So most of these skyboxes come using the HDR format. If you have an older version of ParaView, you'll have to convert the skybox into PNG, but the latest version, you don't need to do that. So that's the example we're going to show. So we show the same torus, but lit using the skybox, and you can see the environment reflected on the object. So let's reset. So you're going to load torus. Super quadric, yeah. So I also changed the values to be more rounded. So basically, you will have to change the interpolation, lighting interpolation to PBR, yeah, and load the skybox. So that's, you do that in the view parameters. In the background, there is a parameter here, skybox, yeah. And then you specify that. That's the skybox I used. I'm going to put all that on the web. So this is the skybox. You can look around. You have to set also use as environment lighting. So instead of using the lighting, the usual lighting available in ParaView, yep, you have 4 light sources. As you see, 4 spots here. You can use the image as environment lighting. So notice that changed. And you can remove the ParaView lights, view, light inspector, and remove that. Yeah. Close this. And also make this more metallic so that you can see better. Okay, so you can see the environment reflected in the, and set the roughness very small. Yeah, and see the environment reflected in the torus. Okay. Okay, so this is PBR, physically based rendering, and image-based lighting in ParaView. We also offer, or we pack together with ParaView, 2 different array or path tracing engines. Intel Osprey, which is open source, but you'll need to run that on an Intel machine or AMD machine, so Intel compatible machine, because it uses vectorization of operations. So this Osprey provides path tracing for Intel machines. NVIDIA optics, that's not open source, and also uses the NVIDIA hardware, so you'll need a NVIDIA graphics card to be able to use that. I have both on this laptop, so I can show you and switch between them, and they provide similar results. Ray tracing supports physically based rendering and also skyboxes. So everything that you've seen so far would work for ray tracing as well, but it supports additional functionality. You can have shadows, reflections, and refractions, and materials as well. So ParaView allows you to do streaming that is set low resolution initially, and when you interact with your data, and then the resolution increases as when you stop interacting. So you can set this using edit settings in enable streaming. Yeah. So try this out. I think it's still it's in try mode, so it's not complete, but it worked for me. So. Okay, so let's look at this example. So this is similar to what we've seen before. It almost looks like before, but if you notice, you have some additional features that you cannot use, you cannot get using physically based rendering. So the additional stuff you see here is that you can see reflections from other objects in the screen. So what I've done here, I just created a number of planes. Yep. So those are reflected in the torus as well as the background. So if you just use PBR, you don't get reflection from additional objects in the scene. You only get reflection from the skybox. So let's try to do that. trying to see how much more time do we have. Oh yeah, so we have about 5 more minutes. So let's try to do that, and then I'll just show you the rest of the examples, kind of how they look, and you can look at them later on, and I'll put the materials on the web after the presentation. So let's try to do this. So we're gonna load the super quadric. And I think I have something else. I have a ParaView state file that loads both the super quadric and those planes. I think this is the one. Okay, so you have the torus and the 3 planes that are also created, yeah? So let's try to set PBR here and also set the skybox. So to do that, we set that on the transform. Yep, so that's the torus. So specify what is the data that you're going to operate on. So that shows you the display properties for that data. Remember, view display properties are associated with data and view. Yeah. So change the interpolation to PBR. Okay. And then change the skybox. Add the skybox to the view. Do that. So this is a skybox. Load this. Yeah. And then use as environment lighting. Okay. So let's set the properties. Let's make this metallic and then completely shiny. Yep. So notice the actual objects. These are the planes in the scene are not reflected in the torus. Yep. So let's use ray tracing instead. So enable ray tracing. You already see this. I use very low resolution here. Okay. Let's see. Takes a while. But you already see that the objects are reflected, yeah, by the torus. Yeah. I should not have interacted with it. Okay. Okay. Yeah. And you can increase the resolution by changing the samples of per pixel. You can use, let's say, 5. Okay, so you get a lot better resolution this way. Yeah. Okay, so let's look at what other examples we have. So we have a few more examples that show you how the fact that ray tracing provides shadows as well as soft shadows, and show you how to change that. Basically, for soft shadows, you need to set the radius for the light to be bigger than 0. And you can set materials, and you can see a reflection based on the type of material you set for the plane. So here I set aluminum for these 2 planes, and I set another metal material for the torus. And then refraction, if you set the material for the torus to be glass or water. ParaView materials are based on Osprey materials. So, and the way they work is you specify the name of the Osprey material, and then you override, eventually you override certain parameters. Yeah. So this is what you do for copper. You overrode some materials from the metal Osprey material. You can, let's see, load new materials, and the Osprey materials are either object materials. These are regular Gouraud shading, provide regular Gouraud shading, or PBR materials. You have a number of materials here. Principled is the most comprehensive one. And this is the last example. I show you ambient occlusion that's available in Osprey Raycaster. You can use that to get a more nicer visualization, especially for like lots of small objects. Okay, so thank you very much. I'll put the slides on the web, and I'll answer any questions if there are any more questions. Thank you. Let's see. Okay. So questions? No, PBR doesn't work on Apple M1. Unfortunately, it only works with the Intel processors because they use vectorization instructions in Intel or AMD. So it works with the Intel compatible processors. I don't know. That's a good question. I think that will depend on Intel. As I said, it uses vectorization operations in Intel, so I'm not sure how easy it would be to translate those. The good news is that this is an open source project, so it could be changed potentially, but it's not. I think it requires some work. So yes, I'll put the PowerPoints. Let's see. Okay, so I think I answered the rest of the questions. Okay, thank you very much, and I'll put the PowerPoints right away.